Hello, hello. Hi, everyone. Um, let's go ahead and get started with unit number one. So today we're only going to tackle two parts of this unit. This unit's small, only has three parts, and the parts that we are tackling is understanding limits graphically and numerically, and then limit laws. Okay, so first, what is a limit? Now, a limit is this sort of approximate value a function takes as it approaches a either constant or an idea. So let's go ahead and just do a little bit of a basic idea. Let's go ahead and do A right away. Let this graph be f of x. A is asking f of -2. Well, we at this point know or should know how to read a graph. And we see -2 here, and we see that that's going to be -3. Now, what does this mean? So this means the limit. It's an abbreviation limit. Limit as x goes to -2. But then we have something that looks like a power, but it's not a power, although it's like on that top right, it's a minus sign. And then if we skip to C, we can also see a plus sign. And then if we skip to D, we don't see anything at all. Well, these look very similar, but they have a clear difference. What is the difference between all these three? Is all of these, -3? No. So let's talk about the minus sign over here. So if we see that we have a limit as x approaches a with that negative looking power of this function, then that tells me that we're looking for the limit of f of x as x approaches a from the left. So, as if we see that negative power, we're going to look towards a from the left. Similar vibe, if we see that power as a plus sign, then we are looking as x approaches a from the right. Now, what if we don't see anything? So this just means the limit of f of x as it approaches as x approaches a. However, if you're not given a direction, you must check both sides, and both sides must match. So let's go ahead and treat this first just visually. We're going to start with B. This reads x goes from -2 from the left because that minus, okay? Do a quick check of what's my left side, and we go from the left of -2. So as I look at this graph and I'm slowly approaching it, I see that my graph will just head towards this value. This value is a 0. How about as x approaches -2 from the right? Well, we're going to go along the lines from the right, and right as it approaches -2, it also seems to coincide with 0. So what is the limit? Well, the limit is both sides, and that both sides must match. Here, we check from the left or from the right, and it is 0, so the whole thing is going to be 0. Does this always happen? Well, not all the time. Remember, it must match. So let's do E. E is f of 0. So I look here, 4. And look here, it says the limit as x goes to 0 from the left-hand side. Well, I'm just going towards the left-hand side. I see that it is also approaching 4 from the right-hand side as well as approaching 4. And the limit is both sides if they equal, and they do, so 4. Now, what's the difference between A, B, C, D, and E, F, G, H's results? The difference is that these match, and these did not match. Does that make this any less incorrect, or does this make this any less incorrect or false? No. We do have scenarios where the limit of a function, as it trends towards a part in the graph, will seemingly go towards a numeric variable. But at that exact instance, At that exact moment, it becomes exactly -2. It does not take place of that variable and maybe has a jump in discontinuity. So keep that in mind. As we think of a limit as x approaches, these values from the left or right, think of numbers on the left or right of them. So, for example, if I'm doing 0, what's numbers left of 0? We got -10, -9, -8. And as we get to -1, we can go smaller. -0.1, -0.01, -0.001, -0.0001, right? And those are all values from the left. What about values from the right? Similar vibe. 10, 9, just go all the way to 1. 1, 0.1, 0.01, 0.001, etc. So please keep that in mind. Let's wrap up this part. We have f of 2. So f of 2 is going to exactly be 4. And then it says limit as x goes to 2 from the left. So from the left of 2, which is right here, we see that it's going to approach 0. From the right of 2, it actually is going up towards 4. So what does that say about the limit of 2 altogether from both sides, left or right? Well, they do not match. So that limit does not exist. All right. Next one. So we got a couple of things happening here. Okay. So f of 2, right? So we're just going to look at f of 2, and we see that it coincides with that value, -1. Limit as x goes to 3. So I'm going to look for 3. 3 is right here. And I see that from the left and from the right, it's going to coincide with that exact same value, 2. This is explicitly -4, but from the left. Well, this one's a trick question because we see that there is nothing from the left of -4. This function seemingly does not exist to the left of -4. So therefore, it does not exist, this limit. Does that mean from the right it doesn't exist? Well, no, because from the right, there's entries that are to the right of -4. So I can follow it from the right and see that it will be the number 2. For f of -1, I see that even though technically it would be here, it is not going to be there, right? So, and it's not going to be there because it's an open circle, not a closed circle. So it does not exist. However, I'm going to jump here. The limit will exist. As we go from the left and from the right, it will seemingly meet up at an entry, the entry being 2. Okay, let's go back in order from 5. Okay, so we see from the left or from the right, it will be 2. As x goes to 1 for this function, it will be -2, actually. From x goes to 4, it's going to be 3. As x goes to -2, from the left and from the right, well, that's just going to be 2. As x goes to 2, we have a little bit of an issue because from the left, it will go -1. But from the right, it will go to 1. Well, those clearly don't equal, so this limit does not exist. And then lastly, for the limit as x goes to 0, that will exist now, being -1. So the limit existence theorem. A limit exists if and only if the left-hand side of that limit and the right-hand side of that limit equal. Okay? So keep that in mind. Now, we're going to now jump into the realm where we're going to approach these limits analytically looking at their equation. So no more pictures. Okay? So this is going to be that increase of difficulty. First, we want to cover 2 baseline limits. Let our f of x function just be a classic x line. And the limit as x goes to a on that x line will just be that a. If we think of a function, right, as that classic line here, well then of course wherever a is, it'll land as an output variable of a as well, as you look from the left and from the right. But if we're dealing with a constant, well, we know a constant function is always going to be, well, frankly, constant. So it doesn't matter on where on x we're looking, the entry will still be that constant. All right. Now we need to find the following limits. Okay. All right. Okay, let's see here. All right. So for our infinite limits here, we have, hold on, give me a second. I want to make sure. Um, just a quick moment. I'll try not to make it too long, but I want to see if maybe my copy is incomplete or if I just left a rogue example 3 set up. No, I just left a rogue. Oh, it was supposed to go above this these two guys. Okay. All right. That's on me. My bad, my bad. Okay. All right. So we will leave the analytical limits into limit laws. I did skip ahead of myself in that, so I apologize. All right. But before we do that, we need to talk about some sort of baseline infinite limit ideas. Now, an infinite limit is deals with both directions. We're going to talk about first when a value as we approach something will seemingly go towards, an infinity, or we'll talk about what happens when x goes towards an infinity. Okay? All right. First off, we have these two functions, f of x and g of x. And we're going to be asked for these limits. Let's start with number one. Number one says, as x goes to 4 from the left. Okay, so I'm going to look at f of x, and it's from the left, and as x goes to 4, it has this up arrow notation. So that leads me to believe that that's just gonna keep going all the way up. So it's gonna be infinity. Then as x goes to 4 from the right. So we're going to 4, but from the right. And that trend line is going down. So that seemingly looks like it's going to go down forever. So it's going to be negative infinity. Okay. Now, as x goes towards negative infinity, so that means we're just going to look left. And we're going to keep looking left. Now, something I didn't say that I'm going to choose to say right now is, what do these dotted lines represent? Well, these dotted lines represent asymptotes. So these are trend lines that we see visually on graphs. So that means that as this keeps going towards the left, that it's going to sort of not reside in that dotted line, but it's going to get as close as it can before it becomes that exact same space in that dotted line. So that means as we go to left, that this guy is going to be -2. And as x goes towards infinity, so as x goes towards the right, it's also going to be towards that -2 as well. How about here? Is this going to be any different? Slightly. Notice how our asymptote is a slant asymptote. So that means it trends just upwards and downwards. Looking here, limit as x goes to 1 from the left. So I'm going to go to 1 from the left. I'm seemingly going down to negative infinity. As I'm going towards 1 to the right, or from the right, excuse me, that's infinity. And then as x goes towards negative infinity, I'm going to go all the way towards the left. I see that I will trend down here, but this is not a horizontal line. It's almost like a function line itself, a linear function line itself. So that seemingly just looks like it's going to keep going down forever and ever. So that's going to be a negative infinity. And similar ideas, x goes towards infinity. All right. Now, from these, we're going to go ahead and talk about certain types of limits. So, or infinite limits, excuse me. So, as x goes to some kind of variable, some kind of entry from the left, and that limit happens to be infinity, this tells me that the y values increase without the bound as x approaches a from the left. So that means that it will, without bounds, without stop, keep increasing up towards infinity as x goes to a from the left. Similar idea here with the negative infinity. It will decrease as x approaches a from the left. We can see similar pattern here for the right and from the right for these infinity values. Here, though, it's a bit different. It's a bit more specific because we don't, or we're not, we don't, what's the better way to say it? Because we aren't given the cue that both sides goes towards the left and the right. We're given that there's just no direction here. So you don't maybe know, okay, well, this means both sides. But we have to remember the definition of this. The definition is that both the left and the right match. So the lack of a symbol implies both sides. That both sides will go towards the exact same value. So as x goes towards a, both sides will go towards infinity. And as x goes to a, and if it equals negative infinity, then both sides will decrease and go towards negative infinity. Let's look at this simple graph of 1 over x. So as x goes to 0 from the left, we will see that goes towards negative infinity. As x goes to 0 from the right, that goes towards infinity. But does there exist a limit as x goes to 0? There does not. They do not match. However, for here, as x goes to 0 from the left of this 1 over x squared, that will go towards infinity. As it comes from the right, that will also go towards infinity. Do they match? That does match. So they will actually, we can actually say the limit as x goes towards 0 will be just infinity. Okay? Now remember this technicality. Infinity is a concept. It's not a number. That's one of the biggest misconceptions about the infinity symbol. A lot of people think infinity is a number, but it's not a number. We treat it like a number sometimes, and I guess sometimes that can happen, but by technicalities, we should treat infinity more of as a concept. The concept being that we are going towards a higher and higher number. And then for negative infinity, just take the higher and say lower. Lower and lower and lower number. Okay. All right. Pretty good so far. The only thing that we need to stress now, let me just double check. Yes. Okay. Now we need to stress now is that this concept of limits, going from the left and going from the right. Okay. That is gonna get, if we don't know that part now, that's gonna get lost on us as we move forward. So please keep that in mind. We want to talk about infinite limits from positive integers. Now, there's this sort of rule setup that we can have here. If n is a positive even integer, then an expression that looks like this will always goes towards infinity. If n is an odd integer, then this expression will go towards infinity, and this expression will go towards negative infinity. Now, what are some key differences? First, they all have the format of 1 over x minus a to some power n. And they're all taking the x towards a. However, for the even one, they don't care what direction, positive or negative. They should both be towards positive infinity. However, From this, we do care about the direction. If it's coming from the right, it's towards positive infinity. If it's coming from the left, it's towards negative infinity. So one more time. The direction here doesn't matter. But if it's coming from the right for an odd integer power, then it's positive infinity. It's coming from the left, then it's negative infinity. Okay. All right. So then we have another technicality. If any of the following conditions hold, then the line defined as x is equal to a is considered a vertical asymptote of f of x. So that means that if this limit as x goes towards a from the left is either positive or negative infinity, or from the right, or all together, we get an infinity, then that means that x equals a is going to be considered as an vertical asymptote. Now, let's start here. Identify any vertical asymptotes for the functions. All right, so let's start here. Well, using this theorem, we can see for this guy we'll have -3. And this, although isn't directly obvious, we can say that that is just x minus and -3. So they share the same a. That means we know that this limit will be infinity, but positive or negative infinity, we don't know. Look at its power. Its power is 3. That's an odd integer. So we have to now look at the direction we're going. Are we coming from the left or are we coming from the right? We're coming from the left. So that's going to be negative. How about over here? From over here, see it's 2 and 2, they match. So we know we're dealing with an infinity. In this case, that's an ugly infinity. In this case, that power is 4, and that's an even integer. So that means that's just going to be positive no matter what direction we're looking at. In this case, we're not even given a direction. So we're fine. How about over here? Well, again, that's a double negative situation. So the A's technically do match. And then that power is 1. We know 1's not an integer easily. Are we coming from the right or from the left? We're coming from the right. So that's going to be a positive infinity. Over here, that's an odd power. So that means we have to, oh, and these A's match. Forget the A's matching. And then we can go ahead and just say, okay, that's going to be an infinity. It's coming from the left, so negative infinity. Okay. And then, hold on. I have a key on the side that I'm just double checking my work as I go along. Okay. Then over here, those A's match. It's an even number, so it's just going to be infinity. Over here, that's an even number. Those A's match, so it's just going to be infinity. Now the second part. So what are the vertical asymptotes? Well, all of these guys follow this rule, where it was either positive or negative infinity based on that exact constant x was going towards. So that means there is a vertical asymptote for all these guys. X is equal to -3 for this one, because that was the a in that one. X is equal to 2, that was the a in this one. X is equal to -5. X is equal to -1. X is equal to 3. And X is equal to 1 for all of these guys. All right. Now, that's going to be it for evaluating these limits. Keep in mind, not to sound rude, but we did not really do anything too mathematical. Okay. We maybe, checked for even and odds and, follow these patterns, but we didn't really stress too much of the math parts. We are going to now with limit laws. So let's go. Limit laws introduce a set of laws for limits, hence limits laws. Let the limit as x goes to a for f of x be defined as L. And let the limit as x goes to a for g of x be defined as M. And let c be a constant. We have the sum and difference laws, meaning if I add these two functions, then I can treat it as two separate limit ideas, where I'm either adding or subtracting them depending on what it started with. If there's a constant, I can go ahead and factor out. I can factor out of the limit altogether. If there's a product, and like I said, these two limits are defined, then that means we could split the limits for their product. So the limit of f of x times the limit of g of x. For the quotient law, similar vibe, you can distribute to the top and bottom of the fraction. Power law and root law are, I want to say, the weirder ones, because this isn't, you can sort of follow these ideas with distribution. These are a bit more niche. Remember, if it's some finite value, then we can technically rewrite this expression as the limit of f of x all to that power. Same thing with the root. Again, if this is explicit, then we can rewrite it as that root over there. All right. So let's use limit laws to evaluate this function and this function. All right. Gonna warn you right now. This part is gonna be really tedious. Just gonna warn you. Okay. All right. Let's go. So we know that via product law that this limit can distribute. So I have the limit as x goes towards 6 of 2x minus 1 times the limit as x goes towards 6 for the square root of x plus 4. Then we know that the limit will distribute to these difference ideas. So I'm going to do a big parentheses to keep them all one product. X goes towards 6 to 2x, and then minus the limit as x goes towards 6 of 1. And then we know that via that root law that it can escape in there. So the square root of the limit as x goes towards 6 of x plus 4. From here, there's a couple of limits we can, or okay, I should say there's only one limit we can evaluate. We can evaluate this limit right away. Limit as x goes towards 6, we talked about constants. So that whole thing's just going to be 1. So I have limit. First, I'm going to use the constant multiple law to factor out that 2. Okay, let me go ahead and just double check my parentheses so we know what the limit is actually attached to. And then minus that 1. And then distribute in that square root. Limit as x goes towards 6 of x plus the limit as x goes towards 6 of 4. Go ahead and evaluate that. That's just going to be 6 exactly. So we have 2 times 6 minus 1. And then we can evaluate both of those limits too. It's just going to be 6, and that's a constant, so that's just going to be 4. So now it's just a classic math expression that we can do. That left multiple is going to be 11, and now it's going to be square root of 10. There's not really much simplifying to do, so your answer is just 11 square root of 10. All right, so that was a bit tedious, but it's important to know what steps are happening, at least with this first example. For the next example, I'm gonna try to be a little bit quicker about it. I'm not gonna force anything to just appear out thin air, but I'm just gonna try to be a little bit quicker about it. All right. So first we distribute that to the numerator and denominator. So limit as x goes towards 2 of the expression 2x squared minus 3x plus 1. And the bottom, the limit as x goes towards 2 of x to the 3 plus 4, okay? I'm going to go ahead and skip that constant rule. We have 2 limits as x goes towards 2 of x squared minus 3 limit as x goes towards 2 and plus, I'm not going to write the limit there, I'll just write 1. We know the limit as x goes towards 6 for the function of 1 is just going to be 1. Similar vibe over here. Limit as x goes towards 2 of x to the third plus 4. Now for here, we can use the power law, which means that we can technically just rewrite this as 2 limit as x goes towards 2 of x. Oh, I forgot to do that, my bad. Minus 3 times 2 plus 1 over, and then again, that power law will happen here as well. So that's going to be 2 times 2 squared minus 3 times 2 plus 1 over 2 to the power of 3 plus 4. Okay, well, that's going to be, what is that? 8 minus 6 plus 1 over 8 plus 4. That's going to be 3, and that's going to be 12. So 1/4. So 1/4 is my answer. Now, keep in mind that I guess if you want to be technical about it, you could solve this limit with a graph. However, we're gonna see for this class that you're not gonna have that luxury all the time. So keep that in mind. You can use the graph to double check your work, but it's gonna be really crucial that you know how to evaluate these limits with the limit laws. All right, now a technicality that I want to address is that we kind of just did glorified inputs, don't you think? Notice how at the end of the day, we just basically, as we process these limits, we just took everything as x became 6 for that top one and 2 for that bottom one. Like, that's literally what we did, right? Does that sort of like devalue what we were learning right now? No. But practicing these laws is important because sometimes we won't have that luxury. But it's not a bad luxury to have, and in fact, it's a necessary one. So that's what the substitution theorem is. Substitution theorem states that if f is a polynomial function or a rational function, then the limit as x goes towards c of f of x is just going to be that function for when x is c, provided the denominator is not 0. Now, you always, for evaluating these limits, want to try direct substitution first. But if you get something like 0 divided by 0, the goal will be to do some sort of simplification. This could be factoring or rationalization, both topics we did talk about in Unit 0. And then try the substitution again. If the expression uses radicals, then multiply the conjugate like we practiced before to cancel out the radical. Now, for this trick, the radical doesn't always have to be in the denominator, and sometimes, and actually today, we're going to abuse just messing with the radical in order to get some kind of determined idea, okay? So, real quick reminder, remember the conjugate idea for doing a radical is just if it's a plus plus or minus the square root, you take the opposite plus or minus value. Or if the square root's reverse, if it's square root plus some constant, you do square root minus that constant. So for example here, we're gonna multiply by 1. But instead of saying 1, we're gonna say the conjugate, which is 1 minus square root of 5 over 1 minus square root of 5. Now, I learned my lesson. I'm going to keep these factored. But this, I definitely have to do a little of that difference of squares idea and distribute. And we get 1, or 1 square, which is just 1. And then minus square root of 5 squared, which is just going to be 5. So it's going to be 4 times 1 minus square root of 5 divided by -4. And that just gets simplified to -1 plus square root of 5. All right, let's go ahead and do these limits, but this time with the idea that we can use direct substitution. Okay, so let's see. First off, this one, okay, that's definitely going to be direct substitution. So we can just plug it in. 2. Okay, it says x goes 2, so we can just plug in 3 times 2 squared minus 5 times 2 plus 4. I'm getting, what is that? 3 times 4 minus 10 plus 4. 3 times 4 is 12 minus 10 plus 4, and that's going to be 6. Okay, very good. How about here? Plugging in x to be e. Okay, well that's going to be ln of e 3e. ln of e is just 1 over 3e. There's nothing wrong with this expression, so that's my limit. Over here we got x4. There's not going to be anything wrong here, but let's go ahead and just evaluate that. 4 plus 4 is all cube root, by the way. Cube root of 8, we know that's just 2. Okay. All right, in this one, it says sine of 2x, 2x of 2 theta, as theta goes to pi over 6. We're pretty sure that exists. This would be sine of pi over 3, and that's going to be square root of 3 over 2 from our unit circle. Okay, all right. For here, I anticipate some problems. Let's still attempt to do the direct substitution idea for these, though. Just, to practice it, we have 2 squared plus 2 minus 6 over 2 squared minus 6 times 2 plus 8. We have 4 plus 2 minus 6 over 4 minus 12 plus 8. We got 0 over 0. Yeah, so that's a no-no. We don't not like that. So we have to do some kind of simplification, some kind of thing to make it work. Now, I do have a luxury hidden in here. The luxury is that I have seen a root appear for both of these polynomials. When I plugged in x to be 2, the top guy became 0, and the bottom guy became 0. So that tells me that that's a root. So I can go ahead and factor out that root. So you can do, AC method if you like, but I'm going to go ahead and do a um, long division, polynomial long division idea. Okay. It escapes me. I forget when. I know in my pre-calc class we talked about division. But I don't know if you guys are coming in with that. So you can factor these by hand, but let me just do a quick sort of explanation of what I'm doing. So we see that 2 is a root of this function. So that means, technically, x minus 2 should somehow divide this polynomial and that polynomial. Let's start with the top one, x squared plus x minus 6. If I divide polynomials, right? Well, you're going to go ahead and match it to its leading coefficient. So you ask yourself, or between the two leading coefficients. So you ask yourself, okay, x times what gives me x squared? Well, x. So you're going to multiply this whole thing by x. We got x squared minus 2x. And then treat it like division and subtract it. X squared minus x squared will be 0. And x minus a negative 2x will just be 3x. Bring this guy 6. Negative 6, excuse me. And then again, ask yourself, okay, what leading guy over here can I get to where I just realized for those of you watching the vertical video, this doesn't matter, but my screen was off. Okay, I just did not notice that till right now. Sorry to all the horizontal viewers. The vertical viewers are your guys are fine. Okay, my bad. Right. Next, x times what gives me 3x? Well, 3. So 3x, and then negative 2 times 3 is negative 6. And those will minus out to 0. So look, they perfectly factored, or x minus 2 can perfectly divide this polynomial. So that means that top guy can be written as these two factors. I'm going to do the other one. X squared minus 6x plus 8. I got x minus 2x. We have negative 4x plus 8, and then minus 4 to, because x times minus 4 would get minus 4x. And also, negative 2 times minus 4 gets a plus 8. So we know that this polynomial could be written as x minus 2 times x plus 3, and that polynomial can be written as x minus 2, x minus 4. Well, we see a common factor, the x minus 2's. So this polynomial technically can be written as x plus 3 over x minus 4. And look, after simplifying, we can see that we can just plug in that x to be 2. Here, I shouldn't write equals. Should do a forward arrow because it doesn't equal, right? But if we replace x with 2, I get 2 plus 3 over 2 minus 4. That's going to be 5 over negative 2. And that's my answer. All right, how about here? Can I plug in x to be negative 3? We have negative 3 squared plus 5 times negative 3. Oh, I don't know why I did that extra line. Parentheses here. I'm doing plus 6 over negative 3 plus 3. Okay, well that bottom's definitely going to be 0. Let's just double check the top just to be safe. We have 9 minus, excuse me, 15 plus 6, and that's also going to be 0. And again, we're left with the sad face. But again, we have a hint. When x is negative 3, this whole thing becomes 0. So that's a root. So we can factor out that root. That polynomial will just be x plus 3. We have x squared minus 5x plus 6. X to get x squared. Subtract 5x minus 3x is just 2x. And x times 2 gives me 2x. And 3 times 2 gives me 6. And that's it. Perfectly factor out. So the top can be written as x plus 3 times x minus, or no, x plus 2 over x plus 3. That'll cancel out.